Hello, welcome to another cosmology talk. In this talk we have Goodhew and Gordon Lee, who are both PhD students at Cambridge. They're talking about cosmological correlators, so the things that when they become observations are things like power spectra and bispectra, and a set of things they call cutting rules, which are analogous to the optical theorem in quantum field theory. These cutting rules are a bit like the positivity bounds that we heard about in modified gravity sometime earlier in the year. And what they are rules on the correlation functions, or on things closely related to the correlation functions, that must be valid if general principles like unitarity and causality are satisfied during inflation. I personally think this is super cool stuff because there are so many models of inflation. It can sometimes feel a bit subjective, picking which one is better and why it might be more well motivated than other ones and things like that. And by narrowing down to these very fundamental principles and saying every model of inflation that satisfies these principles will predict correlation functions that satisfy these rules is actually really cool stuff, just like the positivity bounds is cool stuff. I mean, it goes one of two ways. Either you rule out inflation because you don't satisfy these things, or you do satisfy these things, and in that sense it's a prediction of inflation. Welcome, Harry and Gordon. Do you want to tell us briefly what you did that is described in the paper?
So we looked at a period of the early universe known as inflation, which is the leading paradigm for the production of perturbations that eventually grew into all the structure that we see in the universe today. Within this model, these perturbations arose from quantum mechanical fluctuations in an exponentially growing space-time described by the wave function of the universe. In the paper, we demonstrated the analytic properties of this wave function, and hence all the correlators that are constrained by the conservation of probability. And these constraints allow us to compute observables without the need to perform the often very difficult time integrals that are typically required.
Cool. Okay, so if there were only two things that people remember about your paper or this talk 6 months from now, what would you want those two things to be?
The first thing I'd like people to remember is that fundamental principles like locality, homogeneity, and isotropy place such strong constraints on cosmological correlators that it's possible to calculate the correlation functions directly from these principles via the cosmological bootstrap. The second thing is that we are now understanding the constraints that unitarity places on the analytic constructor of correlators arising from an expanding cosmology that begins in a Bunch-Davis vacuum.
Yeah, so why did this happen now? Why was this work done now? What were the unsolved problems that you wanted to specifically solve? And maybe why did this happen in 2021 and not, for example, 2018?
Well, the motivation for this paper comes in two steps. So to start with, why bother studying the wave function of the universe at all? And then also why study it in the way we study it. So the reason we're interested in early universe physics is because it presents this unique insight into very high energy physics that we can't access in any sort of experiment that we might put together today. So understanding what happened in this period and then the impact that it has on later structure growth is key to developing our theories of beyond standard model physics and the UV completion of gravity. Unfortunately, we have no way of directly measuring what was happening during that time, and nor we have access to our classical probabilities in the data sets that we can measure today. And we believe that they were seeded by this quantum mechanical fluctuations that then imprint themselves on this future boundary of an approximately de Sitter expansion phase. So understanding how the physics impacts those correlators is the way we have of understanding what happened then and what that physics looks like. Rather than looking directly at these correlators, in our paper, we instead focus on the wave function universe. And this is a quantum mechanical wave function that's computed from the action via a path integral. And rather than exploring it in its entirety, because that would be very hard, we instead make this perturbative expansion in these Fourier coefficients that we call the wave function coefficients. These are the psi n on this slide. As you can see from the final relationships here, they fundamentally measure the same things as the more standard correlation functions that are explored in cosmology. So we have the power spectrum, the bispectrum, the trispectrum. And in theory, any endpoint correlator we could also express in terms of these wave function coefficients. But they have some advantages in terms of sort of mathematical structure that makes them more interesting to look at. So the first thing is that when we look at how unitarity impacts the wave function, it turns out that it restricts the analytic structure of these wave function coefficients. And this is done in a way that when we take the real part, a lot of precisely the information that we gained is often lost. And so the relationships then don't hold between correlators, whilst they do hold with wave function coefficients because of the fact that we've had to take the real part. And this is like a non-invertible operation. And then the second reason is a bit more like abstract, which is that these wave function coefficients are reminiscent of the boundary correlators within the anti-de Sitter conformal field theory correspondence. And so exploring their structure could give us some hints towards a similar proposal in de Sitter space.
You might benefit from unpacking what you meant by, I'm not going to be able to remember all of the words as well, but boundary correlators of the conformal de Sitter field space.
So it's related to this idea that in anti-de Sitter spacetimes, we can draw a parallel between bulk observables and a conformal field theory, which is a specific type of quantum field theory with certain symmetries that exists on the boundary of that spacetime. There's lots of interesting maths and physics that you can do with regard to this that lets you look at gravitational systems in a sort of interesting way. And the structure here is very similar to that because these wave function coefficients look a lot like the correlation functions on a boundary quantum field theory. So the kind of idea is that then we can gain hints at a similar correspondence between de Sitter and some kind of quantum field theory.
It's a kind of abstract boundary here now. It's not like an actual boundary of our de Sitter or the inflationary de Sitter space.
The boundary that we are talking about throughout this talk is the future conformal boundary of the de Sitter space that only regards inflation. So this infinite future boundary, which is how we study inflation, is to talk about it extending basically forever. But that boundary is essentially the time slice that is like zero time for the rest of the universe. So these are all correlation functions essentially at the start of the hot Big Bang. And the correlation functions there, this power spectrum and this B3, the bispectrum, they describe the correlation functions on this spatial surface.
And then it's a Boltzmann's code's job to bring that through to be measured in the CMB, for example.
Yeah.
But these wave function coefficients then encode a lot of the information about this bulk behavior. So this exact physics that we're interested in understanding. So what happened in inflation, it's then all compressed in terms of what we can see. So like you said, we evolved those initial conditions with that Boltzmann server from this slice, and we only have that information. That's the only input we need. So we've therefore lost all the information about the time dependence of the theory before that. And what we showed in this paper is that that time dependence imprints itself on these correlators. It gives us information about what these correlators had to look like. And that's similar in thought process to this ADS-CFG correspondence. And so it perhaps suggests a similar correspondence with de Sitter. We haven't actually studied in any real detail this correspondence, but it's a potential reason that we might want to learn more about these wave function coefficients from a theoretical perspective. Okay, hopefully I've convinced you that the wave function coefficients are an interesting object to study. But the other thing that we need to think about is how we then calculate those wave function coefficients. So historically, there have been two ways of making predictions about the universe. So the first is we start with some fundamental principles, unitarity, the equivalence principle, Lorentz invariance, etc. And then we build a model that satisfies those principles. So probably the most famous example of this is Einstein. The way he formulated general relativity was he said, I want a theory that both satisfies the equivalence principle and special relativity. And then that enforced all of the interesting structure that general relativity has. So all the tensorial structure is just a consequence of those fundamental principles. And then from there, we then, within that model, we can compute observables. And we're free to essentially compute any observable we want, given however much computing power we have or are willing, however much time we're willing to put in. This is a really great method of doing predictions, especially when you have a single model. So when we're looking to find out what's happening in the LHC, we want to use the standard model and use that to predict observables. So we have this one model, we can then use it and to calculate Feynman diagrams. However, when we want to be a bit more speculative, so in inflation, we don't really know what the physics is going to be, it kind of breaks down because we don't then have a single model that we can test and compute in. We have to either compute every single model, all the variables in there, or come up with some clever like parameterizations that include lots of different models. But there are also some further weaknesses of this procedure within cosmology. So first is that our results are only valid up to field redefinitions and gauge symmetries if we pick a model. And so that means that the gauge that we might make observations in might differ from the gauge that's easiest to calculate in. And so we just gain additional difficulties. And it also just in general overcomplicates the problem, because what we have is essentially a single object we want to know, and we break that down into all these Feynman diagrams that are all individually very hard to calculate and often end up cancelling between each other. And so we end up with a very simple object that was very hard to calculate. And finally, from a more like theoretical side, if we want to understand how these fundamental principles imprint themselves on observables, by using this model, what we've done is we've obscured that link. So we then only know what the model says about the observables, not what the fundamental principles say. So if we then computed it in hundreds of different models that all obeyed the same fundamental principles or similar ones, we could then maybe see patterns in the observables and work out maybe what's happening, but it makes the process much more difficult. So the approach we instead took is to remove this intermediate step of proposing a model. So we try and directly calculate what the observables are from the fundamental principles. And this is what's known as the Bootstrap approach. And it was used to great effect in the studying of scattering amplitudes. So there are lots of amplitudes that we can just write down directly exactly what they'll be on the basis of the symmetries of the problem. And this is the sort of machinery that we want to adapt to cosmology. So it has several benefits over the model-based approach. First of all, we can simultaneously study all models that you could propose that satisfy the principle. So there are some very basic ones like unitarity and locality that we expect basically any quantum theoretical model to contain. And if we found that our observations violate either of those, then the conclusion is probably inflation is wrong rather than unitarity is wrong. So it helps with that. It then also clarifies the exact link. So exactly what unitarity means for the observable, it then becomes clear because that's the process that we've taken. And then we can gain some extra insight into some non-perturbative things. And then also, it turns out it simplifies calculations. It doesn't necessarily have to, but it turns out it does. And this can be seen, for example, there's a recent paper by Sadra, Enrico, and David, who are some other people at Cambridge, sort of working in our group, where they calculate the one-loop correction to the power spectrum using only bootstrapping techniques. And this is a result that was previously not known. And they had to solve a single first-order differential equation and then apply some constraints. And that was enough to then calculate this result that we didn't have before. So it massively simplified at least that calculation. And so that's the ultimate goal of the cosmological bootstrap program, which this paper is a part, is to establish the process by which we can directly compute the observables from these fundamental principles, and hopefully then constrain the space of allowed correlation functions by this method. The fundamental principles that have proven to be interesting and important are, first of all, we can relate a lot of our results to flat space, which was the kind of key inciting idea as to why we should be able to use everything that was developed within the amplitudes literature. What was found in 2011 and 12 was that this residue of the total energy pole of the correlator is precisely the amplitude of the same interaction. And what this means is that at least at that pole, anything that we can say about the amplitude is also true of the correlator. And so because we have constraints on the amplitude, we then can assume that similar constraints apply to the correlator. And then the question was, do those constraints apply off that pole? So since then, there have been lots of people kind of looking into understanding this bootstrap procedure. This is often, as is in the case of the cosmological bootstrap series of the papers, of which the Arkhani-Hamed et al. And Baumann et al. Papers under the sitter isometries are like two elements of this series. They focused on using the sitter isometries and the constraints that they place on correlators. And they were incredibly successful in finding lots of correlators. However, a result from Dan Green and Enrico in 2020 found that these sitter isometries are, in fact, too constraining for interesting physics. So we can't have large non-Gaussianities in single field inflation models.
What is a de Sitter isometry then? Because if you go back to the other method you were talking about where you write a model and then calculate the expectations, there are lots of models that seem to be consistent with inflation that do generate large non-Gaussianities. So they must not satisfy de Sitter isometries.
It's very possible to write down an inflation model that violates the full de Sitter isometry. So overall, your whole theory should be Lorentz invariant. But the way we study inflation is we kind of assume a background and then have perturbations on that background. And so those perturbations are kind of what we're talking about in terms of what symmetries they satisfy. So just the most general, like P of x, phi inflation models will violate de Sitter isometries in their interactions. And you can see that when you look at the effective field theory of inflation, which is kind of the starting point of a lot of kind of model independent explorations of inflation. And they do have at lowest order terms that violate de Sitter boosts specifically. So that's the main way that we can get large non-Gaussianities, is to break boosts.
What about multi-field models? Or is this all just about a single field?
So multi-field models can be more interesting, even when they don't break boosts. But so specifically in single field models, you have to break boosts to get large non-Gaussianities. In multi-field models, you have a bit more freedom.
Okay, so the results that people found that the non-Gaussianities are small when they satisfy de Sitter isometries were purely in single field.
Yeah. They have some other results that extend beyond that. But that's like one of their main results from that paper. And so what that has led us to is the desire to not include boosts within our Bootstrap program. So when we were keeping all these de Sitter isometries, it wasn't necessary to understand explicitly what locality and unitarity were doing to the correlators, because you could write them down basically without needing to know. Whereas now that we've dropped boosts and we don't have that full constraining power of these isometries, it's become necessary to understand exactly what locality and unitarity say about the correlators. And so that's the kind of the place that this work has within the literature of this field.
Cool. So that's a great intro. Shall we get into the paper now?
Sure. So as explained by Harry, our paper is just one small part of a much larger program, the cosmological Bootstrap program. And our focus is on one aspect of this Bootstrap program, namely the consequence of a unitarity. And the main result that we get is something we call the cosmological optical theorem, which I'll explain further. Again, so let me explain a bit more about what is unitarity. So unitarity more formally means that quantum states must evolve with a unitary time effusion operator. So let's say U is the time effusion operator. So U dagger U must be equal to 1, where U dagger is just this Hermitian conjugate. And more informally, what unitarity tells us is that probability is conserved in quantum mechanics. So you can imagine it's a rather important property to have. Right? Now, it seems very strange that unitarity gives us a useful constraint. So I use this very poor cartoon as a demonstration. So this is the whole inflationary spacetime. Everything we observe comes from the end, CMB and stuff comes from the end of inflation. So that's the boundary. But somehow I'm trying to convince you that things in the middle here, how time evolves, gives you very strong constraint on how the correlators that we observe here. And this may appear to be very strange, but it turns out that it does give you a lot of useful constraint. And to see it, we need to go deeper and write the time effusion operator more explicitly. So U is equal to e to the power I ht, and this where you this interaction Hamiltonian, where you put all your interesting interaction in here for your fields. And again, we remind ourselves U dagger U equals to 1. Now we start working in perturbation theory. So we expand U equals to 1 plus delta U, and this delta U again we express in terms of this interaction Hamiltonian. You put this into here, and what comes out is delta U plus delta U dagger equals to minus delta U dagger. Right. And once you have this, you can just sandwich both sides of this operator with different states, and you get correlators. Right. So this gives you a relation between different correlators. And more importantly, notice that this side, you only have delta U, but this side you have delta U squared. So this is actually a nonlinear relation, and it's rather powerful. It tells you that different orders in perturbation theories are actually linked with each other, and the key linking them together is unitarity.
Wow, that's a nice, clear way of expressing that. Cool, thanks. Yeah.
But of course, to write down our results more explicitly, I'll have to introduce something we call the Hermitian analyticity. And so there's a rather new thing that we found. So let's define something called Hermitian analytic image. So you have a function here, fk. You take its argument to minus k star, and then you take the complex conjugate of the entire function.
What is k star? Is k complex?
Yes, the conjugate of k. Yeah. So if a function is Hermitian analytic, if it is equal to its Hermitian analytic image. So for example, let's say you have a plane wave, right? Classic e to the power ik eta. It is Hermitian analytic because, okay, this fine is Hermitian analytic image, right? You take its function, you take its argument to minus k star. So you get here, right?
But just Real stupid question here. The K in your little green bubble is just a real number, right?
For physical regime, yes, but we usually take continuous things to complex value to see is analytic.
So we're going to apply this to correlators. And so as long as the correlator is a fraction of two rational functions, then it works out and you can just keep this as being a real K. But when you have like logs and things, it's better to slightly deform into the negative imaginary plane. It's essentially a procedure for the way in which you rotate to negative K.
I see. Okay. It is a kind of calculational method rather than a... Because I mean, ultimately, I think this is maybe even a silly conversation because I'm just getting thrown by the fact that you use the letter K, and when one is like observing stuff, K is the wave vector, which is never anything but like a real thing. But of course, it's just a letter, and if you've got a function that is dependent on a variable, that variable can of course be complex.
Yeah, a lot of times you need this to be complex in order for things to converge properly. So in your calculation, so you take this argument to minus k star, and then take the overall function to have a complex conjugate. So you gain an extra minus sign from this I, which removes this minus sign, and you remove this star because you take the complex conjugate of something's complex conjugate itself. So you get back this plane wave. So plane wave is Hermitian analytic, and similarly, you can find a lot of different functions that are Hermitian analytic. Now with this, we have to still define something we call the discontinuity. So it's equal to the function itself minus Hermitian analytic image of some of its variables. So here we notice that this discontinuity operator has some arguments, right? K1 to Kj. So we flip all the K that are not included in this argument. And we also need to flip all the momentum. So this appears to be a rather strange procedure, but it turns out it's rather useful. And we also make one more assumption, that is the field is Hermitian analytic. And it turns out that if you try and look at the discontinuity of a correlator, it can be expressed as the product of discontinuity of simpler correlators, and that's the main statement of our cosmological optical theorem.
Can I just ask a potentially stupid question? So these Ks with like K1, K2, Kj, they are the wave vector of field space, and then your bold K, is that the actual physical momentum in 3 space?
No, the small Ks are the energies, and the bold Ks are the momentum.
Okay, all in field space, not 3-dimensional space.
All in 3D space. So no, all our vectors are 3D vectors, and these are the norms of those 3D vectors. So we're independently treating the norm of the vector and the vector itself as different variables. It's a mathematical trick that we're using. It doesn't have an interpretation in sort of like what you're doing to the variables, like physically, but it's a trick that essentially what is happening is that we are changing the direction of an energy, and the reason we have to complex conjugate everything is to do with our like Wick rotation to keep everything finite, basically.
So K1 is the magnitude of the K vector of field 1, and K2 is the same for field 2. So what is then the bold K on?
This is the collection of all the physical momentum vectors themselves.
So that's what the sum of bold K1 plus bold K2 plus bold K3.
They're combinations of the momentum vector itself. So for example, if you were to look at a four-particle exchange, you can't just express the correlator in terms of the magnitudes of all the external momenta. You also need some like angle, and that's being encoded in those K vectors.
We might just need to, I'm still not following, but we might just need to move on. I mean, what is the difference between K without a subscript and K with a subscript is maybe a more sensible question. I'm not sure.
There should be subscripts in the curly brackets are just saying this includes all possible subscripts that we need to have enough variables.
So this includes, for example, let's say vector K1 and then vector K2. For example, their dot products and so on and so forth. And then this is just the magnitude of K1. Yeah. Okay.
I also want to point out that we're using the word correlator here loosely. It's actually referring to the wave function of the universe coefficient that we used before, but within this entire field, those two words are used interchangeably, which is very unhelpful because they do technically refer to two different things. But just to clarify that the correlator here means wave function universe as I defined it earlier, but it's just an abusive notation that we often use.
Cool. So just one more kind of dwelling question on this curly bracket K. The minus sign in the, the subtracted part, is that only a minus sign for the bits that are like special, or is that minus sign for everything?
Everything, because this is enforced by momentum conservation. You have to flip everything, otherwise momentum is no longer conserved and you start running into trouble.
Okay. I mean, I'm sure there's details I'm missing here, but I think that's been at least a little bit satisfying, and hopefully people can pause and think further if they need to. Thanks.
Let's explain this. I think this can be explained a little bit more clearly if we have something like a graph here. So let's say you want to calculate the wave function coefficient or correlator, and you do it by having a Feynman diagram, right? And then you have some external legs. So this is the external legs, some vertex, and then you have one internal line, S here. You take the discontinuity with the argument S, so you flip everything other than this energy. So what this operator actually does is that it cuts this line apart, and then you get two lines which you push to the boundary. And then this discontinuity just becomes the product of these two correlators, which are easier to calculate. And this is what we call a cutting rule. Everything I've explained just comes from unitarity, and the assumption that we made that is the field themselves are Hermitian analytic, right? Remember. So whether the cutting rules actually works depends on when we have Hermitian analyticity, right? So how do we find out whether a field is Hermitian analytic? So we look at the equation of motion of the field. So for example, let's say you have a massive scalar, right? So the A here is the scale factor, C is the speed of sound of the particle, and M is its mass. So what we found is that we need two assumptions. The first is that mass, the speed of sound, and the scale factors are analytic functions. So clearly enough, especially A, because A is just scale factor, right? And then we also need one more. So we need the Bunch-Davies vacuum, which means that as you go to the far past, the field looks like a plane wave divided by the scale factor. These two conditions gives you Hermitian analyticity. So as long as these two conditions holds for your fields, you get cutting rules, because unitarity we always assume that's true. Essentially, what goes on in our paper is that we look at this equation of motion for all sorts of different fields, and we find that this Hermitian analyticity property holds for field with any mass, any integer spin, and more surprisingly, any flat FLRW spacetime. So the scale factor here doesn't have to be the scale factor of the system. It can be, for example, like some power law, or maybe we actually investigate one particular interesting case. So your background inflation field goes into an oscillating potential, and also weird stuff happen. But this property still holds. So this is a rather interesting result here.
That makes it seem like you could push this past the end of inflation when you do get that kind of, I mean, it's still FLRW, but just not de Sitter.
Yeah, or if for some reason we don't want to look at inflation anymore, but want some other cosmological scenario, as long as you have these conditions, you can still use these rules. So this is rather general, actually.
I will say you look beyond inflation and you start getting strong interactions. So as things like start collapsing, a lot of the assumptions that go in will break down, because we've assumed like a perturbative expansion. It's not quite that general.
It's just more general than we initially thought it would be. Okay, so that is essentially the main result of our paper. We go through the check for different fields, and we find that cutting rules hold for many scenarios.
So people who worked on these kind of vector inflation models, to some extent, it might still be true for them, because I guess integer spin would include spin one, I guess.
Yeah.
So yeah, where do you plan to go next? What is the implication of these results, and how should we in the rest of the cosmology community be changing our thoughts based on these results?
As for where to go next, we intend to, again, this is just a small part of a much larger program. So the natural thing to do is to put everything together and see what comes out of it. So I'm going to introduce something called manifest locality, which is coming from a paper by David, Enrico, and Sadra, which earlier this year. And the idea is that a theory is manifestly local if the interactions are just built from the fields and the derivatives. So for example, this is manifestly local because there's just the field itself and its derivative. This is not manifestly local because it has inverse Laplacian. So there's not the field derivative of this field itself. Now, not all local interactions are manifestly local, but let's restrict our attention to this set of interactions, right? Manifestly local.
What did you mean by not all local interactions are manifestly local? What's a local interaction that isn't manifestly local?
So for example, let's say you work in the ADM formalism and you start integrating out Laplace function. You do this procedure, and then you somehow you start getting this kind of interaction there. The overall theory is local. You start out with by writing something that's local, but then because you integrate out fields, you get things that looks non-local.
So some of the variables that you're now using, which might not be fundamental variables, are themselves non-local, you mean?
No, because some variables that you put in might be just like constraints and stuff. So you want to do some procedure to remove them, right? And for example, you want to just integrate them out or just choose some gauge. And turns out that in doing so, you sometimes introduce things that looks like this. We try and look at this manifestly local things for master particles, and they managed to derive something called a manifestly local test. So this is the wave function. You take the derivative of its external energy and then set that energy to 0. If this is equal to 0, then the interaction you have must be manifestly local.
Is there a heuristic way of seeing that, or is that something we just have to kind of take?
The idea is that the solution of a master's field looks something like this, right? And then if you form your interaction by putting together these fields, so they clearly must have all sort of vectors from these things, right? But if you expand it, right, this becomes you expand this, it's become 1 minus, and then this becomes 1 plus so on and so forth. These two cancel, so this becomes 1 plus, and then things start at k squared, etc. Because they start at k squared, so this derivative must be 0.
Okay. And yeah, all right. And if it wasn't local, then the top line of your working wouldn't necessarily be the correct.
Yeah, because things don't necessarily just form from products of these or their derivatives. It turns out just by imposing manifest locality and with both symmetry and scale invariance, you just start with 3 principles. It completely fixes the bispectrum or the 3-point correlator of your master's theory. Just these 3 principles. So it fixes it to be a polynomial of these either the total energy or these combination of the energy divided by total energy to the power p. This p depends on the derivatives you have in your interactions. But so this is already very powerful, right? But what happens if you combine this with unitarity, right? So it turns out what unitarity gives you is that it fixes all these partial energy singular behaviors in your correlator. So for example, you have an exchange diagram like this. It tells you must have a pole when EL, so the energy, total energy at this vertex, K1, K2 plus this S here, internal energy equals to 0, or ER, so the energy on the right, K3 plus K4 plus S equals to 0. Unitarity tells you that it must have poles here, and then you combine this with locality, and this tells you what the residue of that pole must be. So in some sense, you are reversing the process of cutting correlators, right? You are finding the discontinuity of a larger correlator using simpler correlators. You're putting simpler correlators together to form larger correlators. And you can imagine, right? Once you have this, you can just treat this as another correlator, which you then glue to another new correlator. You just do this recursively, and this pretty much fixes your entire theory at tree level. What happened in our paper is that we managed to extend this to, well, spinning fields. So now we can try and do the same story, but for master spinning fields, and in particular graviton. Because you can imagine maybe some future surveys on gravitational waves may give you some information on primordial gravitational waves. And looking at the correlators might actually give us a better experimental understanding on inflation and stuff, and tell us a lot more.
But when you say looking at the correlators, you're meaning like on the observational side, you're meaning like bispectra and stuff of a primordial gravitational wave signal. Okay, I guess that's ambitious.
Well, even the power spectrum is so. For example, one of the things that can be fixed by this is the like loop corrections to the power spectrum. So the power spectrum itself is also like in the domain of what we've computed. So if we had the information to look at the bispectrum, that would be amazing. But
yeah, of course, that might be very far away. But
well, history is still full of situations where people thought something was completely unmeasurable, and then it turned out that there's a technological breakthrough that makes it measurable. So I can sit here and go, ha ha ha, you'll never measure the bispectrum, and then be embarrassed 8 years from now when observational bispectra of the primordial gravitational waves is the cutting edge of cosmology. So it's definitely worth calculating.
But there's another thing about gravitons that's special. The solution to its equation motion is pretty much the same as the master scale case. So a lot of the understanding of manifest locality immediately applies to graviton. And there's a lot of work that can immediately be done on graviton. That's one thing that you can do. The other thing we can do is to essentially try and connect it with the whole positivity bound story. I don't know if you've heard of it before. So
I had a talk on positivity bounds in the context of modified gravity, where they did talk about positivity bounds from unitarity and locality. Not everyone watches every single talk, so maybe summarize it again. But if people like this, then they should go watch that talk as well.
sure. The main idea is that not every low energy theory can be UV completed to a high energy UV gravitational theory. So you can ask, let's require the UV theory, the high energy theory, to obey some physical principle, again, like unitarity and locality and stuff. And you ask, what does that tell you about the low energy theory? And it turns out that you can write down a surprisingly large amount of constraint on the low energy theory. And we can actually look at our correlator to see whether it can be properly UV completed, or maybe just see how we can connect this whole story with the positivity bound story. And of course, there's one more thing that we could do, we should do, and in fact, I should say this, we should do, is that we should extend this to beyond perturbation theory, because so far we have just been talking about Feynman diagrams and stuff. But we know that in particle physics, there is an optical theorem that is non-perturbative, right? That's the one that tells you the total scattering cross-section is related to the imaginary part of the scattering amplitude, that kind of stuff. Now, first of all, it will be interesting to see the analog of this for cosmology. And second, it would be very interesting to see whether it can place some new interesting constraint on perturbation theory. For example, whether it breaks down at some level so that we can introduce some new UV physics to complete everything.
Interesting. In general relativity, beyond perturbation theory is a very significant thing, right? Because then it could be any metric, right? Whereas in particle physics, I can kind of see where beyond perturbation theory is not necessarily that open a space of possibility, I guess.
Yeah, it's exactly beyond perturbation theory where the interesting gravitational stuff starts to come in. For example, you have the black holes, right?
That's exactly what I was thinking. Like beyond perturbation theory of FLRW would include a black hole.
Yeah, once you start with black holes, you start getting all sorts of funny things, especially if you're trying to into the quantum side of the story. You start getting like information paradox and stuff like this.
Yeah, like local horizons inside your space rather than.
So if you think about it, right, the zeta space also has a horizon, right?
Yeah, but it's sure, but you yes, but it's kind of far away from you.
It is far away from you, but some of the ideas might be the same. Maybe for example, maybe it also, because it has a finite area, so it also has a finite entropy. So this might tell you at some point perturbation theory might break down. So all of this is very speculative.
It'd be very interesting if you found constraints that go beyond perturbation theory, because exactly what you're saying, they'd be very far-reaching.
It's very far-reaching, but I think it's an exciting thing that we should explore.
Just trying to bring what you've been saying into what would it look like for observers to see something that is an interesting consequence of your work. So maybe you can answer that very general question, but I'll give you a specific question as well. So what would it look like to measure something and then from that measurement go, oh my gosh, unitarity has been violated if inflation is true? What would be the measurement that would show that?
So our constraints are initially on non-physically observable things. So for example, what we were talking about before, when we're not even just like taking the complex conjugate, but the fact that we've had to go to negative k to like define our result. It means it's not a result for the physical correlators. But what you can do is, using Cauchy's theorem, is relate that back to then constrain with some extra assumptions. So the most important one is that there are certain poles that we don't want to have. We don't want there to be a pole when like k1 plus k2 minus s is 0, that kind of thing. Because that's like a physically realizable pole, so then we'd have like weird divergences in the correlation functions. We'd say, as long as we don't have those, we can use Cauchy's theorem to then relate our result directly onto physical observables. And then those are things we can say, the only correlation functions that are allowed are these at this order. At the moment, we can only do that for theories that are analytic up to some poles, because we're using Cauchy's theorem. However, if we want to include massive particles in our cosmological collider, then we don't yet know what to do, because you end up with non-meromorphic functions.
Okay, I'm not sure what meromorphic means, unfortunately, but
you end up with functions with branch cuts all over the place. If you just want the simplest way of getting a thing with a branch cut is to look at a lambda phi cube interaction in the system, and then you end up with logs. Even in a single master scalar field, you end up with logs. But that's not something that we expect to have in the like spectrum. We don't expect to have a phi cube interaction. It doesn't appear in the EFT of inflation. So that's not too concerning. But then when we look at things involving massive fields, we again pick up logarithmic divergences in the momentum. And so in that case, we don't know how to actually get our results out of this non-physical place.
Okay. So the short answer is that's kind of an unsolved problem at the moment.
You could make an observation at the moment that would say what we see in inflation is not compatible with a single massless scalar field and unitarity. So we do have that. There are certain correlation functions that are not compatible with a single massless scalar field.
So what would such a correlation function be?
I don't know off the top of my head what the, as in this is some like function of momentum, and there are like combinations of those that you'd have to like plot all that whole space of dependence on your different.
Oh, and you mean it could also be that like it's that the trispectrum is bigger than the bispectrum over some range or something like that. It's not just one function. It's
Well, what I mean is if we look at the bispectrum, there are only certain functions of the momentum involved that are allowed as functions, but then actually saying that, like converting that to an observable statement is a bit harder because you'd have to then say, okay, this is then an allowed shape, but that then corresponds to like something else in terms of like comparing it to observations at the moment. I think that's the stage at which it breaks down in terms of a direct saying. We could right now say that single field inflation is wrong. I'm not claiming that. I'm saying that if you gave me like a perfect measurement for all values of K1, K2, K3, you could say obeyed these constraints.
Yeah. So, but it is something that is conceivable in the future, like 5 years from now, that it will be at that stage.
Yeah, that you could express these constraints for any scalar field. Yeah, and then say this is not compatible with unitary inflation. I think that's conceivable. It might be harder than something that can be done in 5 years, but
okay, yeah, 10 years. You guys will have your PhD students solving it in 10 years' time. What work being done in the cosmology at the moment do you think is particularly underappreciated by the rest of the community?
I would say that this bootstrapping type of thing, not necessarily just outside. I know of some people that are trying to actually do it for some late universe observables, for example, like dark energy, dark matter perturbation, that kind of thing. I've heard of people doing that kind of stuff, and I think people should probably pay more attention to those work, and because this is actually rather interesting to me, at least.
It's not exactly cosmology, but I think so. The study of analog gravity systems, I think it's something that's quite underappreciated, especially in its ability to like reveal general features of a space-time. And to relate it back to cosmology, most of the phenomenology that's been observed is like black hole analogs, but there are proposals for cosmological analogs, which could be especially interesting in light of the sort of things that we've been looking at in terms of these are really generic properties of spacetimes. And so if they can then be observed within an analog cosmology, I think that would be a very interesting way of gaining insights into sort of what the early universe could look like.
By analog cosmology, you mean like fluid flows or cold atoms or something that have similar equations to,
yeah,
like a black hole is water going into a sink and stuff like that. Is that?
Yeah. So in exactly the same way that you can see black hole phenomenology in a draining bathtub, it's the setups are much more complicated than for black holes, but you can do things like magnetize liquids to then make them to produce particles in the same way as inflation does, and have it like look like it's growing.
And then you would have all of the things like consequences of these bootstrap principles would be there. Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with the YouTube algorithm, and share the channel with your colleagues. If you have any questions, please leave a comment and I'll make sure that Harry and Gordon see them. And other than that, thanks again, Harry and Gordon, for a great talk.
Thank you.
Thank you for having us.